Sequences are incredibly important because they are the building blocks to discovering patterns over repetitive iterations. This has huge implications for computer science and engineering. Let's take a look at one mathematical application, partial sums. It is possible to construct a sequence by adding terms from another sequence. Let's take a look at an example together. Sam keeps track of how many push-ups she does each day of her Do Lots of Push-Ups challenge. Let an, starting from n equals 1, that's important, be the sequence that describes the number of push-ups done on the nth day of the challenge. The sequence starts 3, 5, 6, 10, 9, 0, 12. Describe the sequence bn that describes the total number of push-ups done by Sam after the nth day. We can find the terms of the sequence easily enough. So we start with 3 push-ups. This is for bn. We start with 3 push-ups, and then on the second day, by the end of the second day, we will have done a total of 3 plus 5 push-ups, which is 8. And then we'll have 3 plus 5 plus 6, which is 14. And then 24, and then 33, and then 33 again, and then 45, and so on. So here, B1 is just the same as A1. But then B2 is going to be 3 plus 5, which can be written as A1 plus A2. And then B3 is going to be A1 plus A2 plus A3, and so on. There are a few ways we might describe Bn in general. We could do so recursively as Bn equals Bn minus 1 plus An. Since the total number of push-ups done after n days will be the number done after n minus 1 days plus the number done on day n, which is exactly what this is conceptually. So for the close formula, we could write that Bn equals A1 plus A2 plus ... all the way up to An, or the same thing using some summation notation. This is sum from I equals 1 all the way up to n ai. However, note that these are not really closed formulas, since even if we had a formula for an, we would still have an increasing number of computations to do as n increases. Given any sequence an, we can always form a new sequence bn by bn equals a1 plus a2 all the way up to an. Since the terms of bn are the sums of the initial part of the sequence an, we call bn the sequence of partial sums of an. Soon we will see that it is sometimes possible to find a closed formula for bn, a nice little neat formula from the closed formula for an. So to simplify writing out these sums, we will often use notation like this. This means add up all the AIs where I ranges from 1 to n. If we want to multiply the AI instead, we could write out this fancy looking capital pi from I equals 1 to n AI. And again, this is A1 times A2 times A3 times ... times AN. So for example, we could use this notation to write out something like this from, let's do k equals 1 to n k. And then this would be 1 times 2 times 3 times all the way up to n, which we know the definition for that. This is n factorial. So that's another way of writing n factorial. So you can do the same concept with partial sums with partial multiplications, if you want to call it something like that. Anyways, thanks everyone, and I'll see you in the next lecture.